A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. So, a few of you were asking about the mind map, and you put the name of brainstorming in that. So, I will provide you a basic kind of a flow pattern about how this entire formation did happen. So, you had around 5 billion years back, or 4.5 billion years ago, you basically had collision of dust particles. Then creation of planetesimals. Then after that, formation of protoplanet. Proto means the primitive form, the earliest form. Formation of protoplanet. Molten earth. Then you had the giant impact. That is what led to the creation and formation of moon. Then after that, you had the cooling down. Earth began. Then came the phase of degasification. That is a period of volcanic eruption. Then after that came the formation of thick clouds. Then came phase of torrential rainfall. Rains. Formation of the blue planet. Of blue planet. Roughly around 3 to 3.5 billion years back, then you had the genesis of life. So that was the entire creation, the process of creation, and the various different stages involved in between. Now, Parshuram, you have a question, and yes, the question is the same layers are present in the moon as the Earth? No. See, think about it. Understand this particular thing, guys. And this doesn't require much of a logical application. This is a simple part of common sense application. If you have a sphere, a large sphere, now some materials have basically some of those materials, they have already concentrated around the center, right? Iron, nickel, etc. Now the other materials, and it at this point of time, if a collision happens in this region, only the layers which are present, only the materials which are present in this area, along with the materials of Theia, some of those materials, only they will end up forming the new moon, isn't it? The materials which are present in the interior, the other layers, they won't be forming a part of the moon, is it? So that is why the lunar body that you observe consists of few portions of the upper regions of the planet Earth, the molten planet Earth, along with the remnants of Theia. Okay, is that clear? Any doubt which persists, guys, till now? Any doubt? So I think geography is a very assumption based subject, because who was there to watch many years ago? That is very, very true. For that matter, in geography, when we talk about a few years back, we are basically talking about few thousand years back, right? In other subjects such as history, etc., when you talk about few years back, you're talking about maybe 20, 30 years back. In subjects such as polity, when you refer to few years back, you are talking about 3 to 4 years back. So that time scale also ends up varying. It is only lately, that is in the 1900s, and much more to be precise, after 1950s, when all that scientific advancements happened, that is when we started studying the rocks. And in fact, one of the Apollo missions, in fact, the Apollo missions, I'm sure you would be aware of the Apollo missions which put man on the moon. So one of those Apollo missions brought back samples from the moon. Only after studying those samples did we get to the realization that, okay, this is also a part of, or the materials are very much the same which forms the part of the planet Earth. So that is when the hypothesis of giant impact came into existence. So if you observe the research papers from the 60s onwards, that is where path breaking discoveries, they keep on happening very, very frequently, obviously because of growth in scientific advancements. Now we have the ability to even estimate what would have been the condition of the universe at the time when the giant impact happened, what would be the energy which would be created. So slowly and steadily we are getting much more precise in our prediction method. But again, what you are saying is to the point, and that is something that I convey to all the candidates. Geography is a subject where the better you are able to imagine what would have happened, and for that imagination you don't have to close your eyes and think about a cartoon world. That is something which behaves in a simple way, like how the water behaves in a glass. When you put water and oil, they will separate with each other depending upon the density. So those basic principles of science, they are the ones which have driven the entire formation of the universe and the formation of the planet as well. Torrential, what is torrential rains? So torrential basically means the kind of a continuous and excessive repetition of a particular event, right? For example, a torrent of questions. So you had a torrent of questions which were put forward. So a series of questions which were put forward. So that is what is the meaning of torrential here. Torrential rains means you had a phase where it rained continuously for 7,000 to 10,000 years. Few of the scientists have even went ahead to say that it rained continuously for 2 million years. But obviously, we don't have enough evidences to support the same. Okay. And Ganesh, is volcanic eruption happening in moon and gaseous formation? No. In moon, you did not have the phase of degasification because it was much smaller object. Cooling down happened significantly quicker. And in fact, the craters on the moon that you see is because of the collisions with the outside objects which came and collided with the moon. Okay, I hope that is understood, right? I'm on difference between geology and geography. Geology is a subpart of the larger portion of geography. Geology overall, if you think about it, it is concentrated upon the study of the rocks. Logy, right? Logy refers to the study of it. So study of the ground realities of the rocks, the land surfaces, the nature, the chemistry of the rocks. That is inclusive in geology. In geography, you look at the larger picture. In geology, you get into the intricacies of it, that what kind of chemical reaction can lead to the crystal formation, what kind of spacing will be there between the atoms, that can give us an idea about where these rocks would have been formed. And the geologists, they basically are able to understand, just based upon the atomic structure, that whether this material has come from the region of let's suppose lower interior mantle, or from the closer to the surface. So that is the portion of geology. Okay, that is why almost everything is a theory. Yes, Nikhil, absolutely. So Are we comfortable? Can we proceed ahead? Or is there a point of discomfort in any of the portions? Please let me know. See, in the portion of physical geography, in the initial classes, I am going to give you as much time as you want, because first of all, I also understand many of you are basically interacting me for the with me for the first time. Many of you might not be used to the methodology that I use for conveying a certain set of information, so it will take some what we refer to as the teething problems. So initially I am ready to give you as much time accommodation as much as possible, but ensure that the questions that you ask after you have paid due attention. I will never tolerate any question which is asked just because, I missed the previous portion, I was not attentive enough, so now repeat that. That is something which won't be tolerated. If you have paid attention, if there is a genuine doubt, you are unable to understand, I'm ready to repeat it as many times as possible, unless and until there is some other issue associated. Okay? So now we come ahead to the portion of the interior of planet Earth. Now, what constitutes the interior and what is present in the interior of the planet? This is again a kind of a puzzle which has basically confronted us for a very, very long period of time. As I told you in the initial stages of the class, that in the initial stages, mankind always thought that we were inside the planet Earth. It was a kind of a giant sphere under which we are living. So we were always intrigued about what is this planet, what this planet is constituted of, that sometimes you see molten materials coming up from underneath, right? Sometimes you observe that the land in itself parts ways and water comes in between. Where is that water coming from? All those factors have continuously intrigued us. But the knowledge and information about the interior, that eluded us substantially up till the uh, 1800s. It was only in the 1800s when our understanding significantly increased. By the way, a minor correction. One of you had pointed out that earlier I had mentioned that Kant provided his theory in 1600s. It was in 1700s that Kant and Laplace, they provided their theory. That is a minor connection. But other than that, coming back to the portion of interior, so the information about the interior that started coming up when we started observing the volcanoes and the earthquakes. These gave us a lot of idea, lot of information. And also the study of meteorites, for example, the ones which fall on the planet's surface. Now that also gave us an idea about what kind of elements would be present in the earlier state of the planet Earth. And upon meteor collisions that we observe in other parts of the solar system, other parts of the universe, that gives us an idea about what could have happened 4.5 billion years back. How is it that the planet got created? So now, thankfully, we have a substantial bit of information about the interior of the planet Earth. Now, how do we get that idea? So that is based upon certain sources of information. So the sources of information for getting an idea about the interior can be divided into two parts. Can be divided into direct sources and can also be divided into indirect sources. Direct sources means first hand we get an idea about the various different material or the information about the interior, the first hand idea we get. So direct sources include volcanic eruption, because in the case of volcanic eruptions, material from inside they come up. Which portion of interior we don't know, but some portion from the interior they come up, right? We will study more as we go ahead into the portion of volcanoes, but as of now we do know that something from inside comes up during volcanic eruption. By studying those, we get an idea about what is present in the inside. So that is one of the sources. Other sources, by digging and mining. Now, when we say digging and mining, it is not as if we are able to dig through the entirety of the interior of the planet. Even by digging and mining, we basically restrict ourselves to the top portion itself. Because when we talk about the entirety of the planet, the radius is somewhere around 6370 kilometers. So approximately the radius is close to around 6400 kilometers. Think about it. Twice the length of the Indian subcontinent and some more than that. So that is the radius, not the diameter, radius of the planet. Till now, the deepest mine that we have been able to dig is present in the Kola Peninsula. Kola Peninsula is in the northern part of the Eurasian landmass. So in that Kola Peninsula, the deepest mine is around 12 kilometers deep. That is the deepest mine. But there also, we get an idea about the change in the density of the rocky types, the rock materials, etc. That information we can get, how the temperature starts increasing as we go into the interior of the planet. So that basic source of information we get from this. Recently, we get the idea that China has been digging massive holes underground of significant amount of depth to gain an idea about the interior as well. So these are basically the scientific works. Then comes the indirect sources. When we talk about indirect sources, here, one of the major and most important indirect sources is the study of earthquakes or the seismic waves. So, whenever an earthquake occurs, energy is released from the interior, right? That energy, which is released, after all, that is the energy which leads to shaking of the ground surface, etc., the falling of the buildings, and so on. So, that energy which is released, that energy is is something which travels in the form of a wave pattern. That is what we refer to as the seismic waves. So those seismic waves also give us an idea about these particular indirect or about the interior of the planet Earth. When we study about earthquakes in the next module, we will get much clearer picture about what these seismic waves are, the type of seismic waves, and how do they help us understand the interior of the planet as well. Then study of meteors and meteorites. Then, because study of meteorites, they will give you an idea about the particles, the elements which were present in early solar system, in the early universe, at the time when planet was not even there. So many of these asteroids, meteors, meteorites, etc., so they give you an idea about what would be the constituents of the early solar system, the particles which would have formed the planetesimals, what would be the elements present in them. That is why these are studied. Then magnetic and gravitational anomalies. And gravitational anomalies. So when we say magnetic and gravitational anomalies means, so let's suppose you have a particular the when we consider the planet Earth also exhibits its magnetic field, and that magnetic field, it ends up indicating different pattern in different areas. So that also gives you an idea about what is happening in the interior. Because as we will study later, I will talk about geomagnetism. The magnetic field extended by the earth is called as geomagnetism. So that geomagnetism, why it is subtended and where it is in existence, that is something we'll study later on, right? But gravitational anomalies, what do we mean by that? So planet earth is not a complete sphere. If it would have been a complete sphere, gravitational pull of attraction at all different places would have been the same. But it is not a complete sphere in the sense that in certain areas, that is around equator, there is a kind of a bulge. Around the region of the poles, there is a kind of a flatter portion that you observe, right? So wherever you observe the kind of a bulge, obviously distance from center is higher, so there will be lesser gravitational force. Whereas in the poles, because it is slightly, very minutely closer to the center, because it is flat, so the gravitational pull of attraction is slightly higher. So that change or the variation in gravitational field, that helps us understand the shape and also the interior. Okay. Now, uh, here, after this, we come to the basic portion, that when we talk about, let's suppose, the idea that we have gained about the interior. So over a period of time, we have gained plenty of idea, plenty of information about what is constituted in the interior. We also know that there is significant and substantial amount of residual heat which is still trapped in the interior. As we move across to the depth of the planet Earth, the temperature indicates an increase, in the sense that every kilometer deeper that you go, the temperature can increase by 20 degrees, 15 degrees, or 25 degrees Celsius as well, for every kilometer, right? So it is not consistent, but somewhere in that range. That is what is also referred to as geothermal gradient. Geothermal gradient. Now, geothermal gradient basically means or indicates increase in temperature experienced as one moves in the interior depth of the planet. Okay? Experienced in the interior depth of the planet, that is geothermal gradient. Now, when we talk about the portion of the interior structure of the planet, overall, the structure is divided into crust, mantle, and core. The region that we live on, that is the thinnest portion of the planet Earth, that is the crust, right? Then you have a solid amorphous compressed, that is mantle, very bulky. Then you have the core. So in the core also you have the outer core, which is in molten state, and then you have the inner core, which is in solid state. Now temperature keeps on increasing. If you have to form an analogy about the structure of Earth, the best analogy will be that of a coconut. Other than the inner core, the rest of it will follow the analogy of a coconut. Now all of you would have witnessed coconut. Now coconut, the outer shell of it is hard, but it is very thin as well. Then comes the internal fleshy portion. You compress it, it can be compressed, but it is bulky. And then comes the inner liquid portion. So here also, the outermost crust is hard, but it is very thin, right? It is the thinnest portion, represents only the crust that we see, the crust that we live on, represents only 1% of the mass of the entirety of the planet Earth. So you can think about it. You can understand how minute that is. And the mantle, which forms bulky portion, that is the fleshy portion of coconut that you see. So it is solid. Mantle is solid, but basically it can be compressed, and over a period of time, due to heat, residual heat being released from the interior of the core, you have that mantle sometimes changing shape, getting molten, rising up, sinking down. So these events are something that you observe in the mantle. Now, here, when we talk about the region of the core, outer core is liquid or molten because of very high temperature, but inner core is in solid. Why is that? Despite the very high temperature, inner core is in solid state. Why is that? Beautiful, Krishna. Due to pressure. Let us understand that concept. Let us understand why the inner core is in solid state. So for that, I would take you to a blank slide here. And basically, I want you to again think about one of the basic things of science that you would have studied. So if you have, let's suppose, a particular material such as any of the materials that you consider, iron, aluminium, any solid material. Now, in this case, when it is solid, that is when the atoms, they are absolutely, and the molecules, they are packed with each other in very close contact with each other. always, isn't it? But when you heat it up, for this to melt, the atoms and the molecules, their internal bonding and the structure will have to weaken, because in liquid the molecules are further away from each other. So for this to get converted into liquid, right, after applying heat, if it gets converted into liquid, what will be required? It will lead to expansion in volume. Expansion in volume, right? For other than ice, I'm not talking about ice, but for other materials, if from solid to liquid they get converted, there is a requirement for expansion in volume. Now imagine, if let's suppose I have a particular material which is in solid state, right? Now from all different sides, I am restricting this material here. From all different sides, I am basically providing enough pressure that this material cannot expand in volume. Now, in case I increase the temperature continuously, but there is no space for expansion in volume, so this solid substance, will it get converted into liquid at all? Never. It will continue to remain in solid state regardless of how high temperature you take. It will continue to remain in the solid state itself, right? Because for conversion into liquid you need some expansion in volume. So that means if there is no space to expand, if there is so much pressure that there is no such space to expand, the materials will continue to stay in the solid state regardless of the high temperature. Something very similar is at play when you talk about the portion of the inner core as well. So, in the inner core, observe that from all the surrounding areas, the pressure exerted by these thousands of kilometers of rocky areas, so when one rock is put on something, you can think about the pressure exerted. Imagine thousands of kilometers thick rock when they are getting imposed on the inner core. The pressure would be extraordinarily high. So there is no space available for liquefaction and further expansion. So that is why it continues to stay in solid state. So here, due to pressure from the overlying layers, right, as there is no scope for expansion, inner core continues to stay in a liquid state, or rather in a solid state. In a solid state, despite very high temperatures. Okay, this is the reason why the inner core continues to remain in a solid state as compared to the region of the outer core. Okay, I hope this is a portion which is clear. Now, when we take a look, the thinner core is solid, inner core is solid due to the pressure from above layers. Yes, Sherlin, that is correct. So that is basically the reason for the variation in terms of the state of matter in which they are present. Now, when we talk about the planet structure, when we talk about the layering of the planet. So crustal layer is the thinnermost portion. The crust that we observe, that extends for almost 30-35 kilometers, in certain cases, very rare cases, 70 kilometers from the surface, but that is it. That is where the crust ends. Now, the crust, if you think about it, that is going to have a thin portion. Then after the crust, you have the region of the mantle. This is not a correct depiction, however. So the crust is very, very thin. Okay. Now, then you have the larger mantle. Now, the mantle overall is in solid state, overall. But then, after a particular depth in the upper portion of the mantle itself, there you do find the presence of semi-solid, plasticky, semi-liquidy state, neither a complete solid nor a complete liquid. That semi-solid basically layer is present in the region of the mantle. There is some portion of solid mantle above that as well. There is significant portion of solid mantle below that as well. But in that region, you have the semi-solid plasticky. That is, when you melt plastic, it is not a complete fluid. It can be stretched, right? Partial fluid, partial solid. That kind of a semi-solid state is there. Now, this is what is referred to as asthenosphere. Asthenosphere. It is derived from the term astheno, which refers to weak. This is semi-solid or plastic. Above that also, portion of upper mantle, you have solid upper mantle. Below that also, you have solid mantle. So, this portion of crust plus upper solid mantle, this is what is referred to as lithosphere. So here the question which begs an answer is that if the region of mantle above asthenosphere is solid, if the region of mantle below asthenosphere is solid, then why is it that the asthenosphere is in a semi-solid or a semi-molten plasticky state? There is a reason for that. Because at these great depths, we are talking about a depth of 160 kilometers to 400 kilometers. That is the depth that we are talking about. Okay, so the upper margin of asthenosphere can be around 160 to 200 kilometers, right? And the overall depth is 160 to 400 kilometers from the surface. So in that region, you do have the presence of certain radioactive materials. Which radioactive materials? Materials such as potassium, materials such as uranium, right? So these radioactive materials, owing to the pressure exerted by the rocks on top, and also as you start going into the depth, the temperature starts increasing. So these radioactive materials undergo a nuclear reaction, thermonuclear reaction. Whenever nuclear reaction happens, lot of heat is produced in the process. So that is what produces significant amount of heat, and that heat partially melts the materials present in that area. So here you will observe, good Ravi. So here in the region of asthenosphere, you have the presence of radioactive materials like uranium, and potassium. They undergo thermonuclear reaction thermonuclear reaction in that thermonuclear reaction heat is produced and that heat partially melts the materials in the layer. Okay, uranium is a part of this layer? No. So uranium that you see being extracted on the ground surface, etc., being used for nuclear energy, that uranium is present on the ground surface closer to the crustal layer in that itself, on the top surface closer to that itself. But when we talk about the asthenosphere, there also uranium is present. That is also uranium which is present at these depths. We don't extract uranium from these depths. I hope we are able to understand what the deepest mine that we have dug is only 12 kilometers, right? The deepest mine. And there also people could not go beyond a certain point of time because the temperature would be so very high. Water would start boiling, people would die immediately. So that mine was also abandoned. So all that groundwater, etc., that you see, mining, etc., exploration, that happens within a few hundred meters from the surface. We are not even scratching the lower portion of the crust when we talk about these mining activities, right? So we till now we have not at all managed to reach the layer of mantle at all. We have at max reached the region of lower or middle crust, not even lower crust in many of the cases. Okay, and that perhaps will also give answer to your question, Srimant, that can we say ocean touches the mantle? No, we cannot say that. Is potassium radioactive element? Isotope of potassium, it is radioactive, yes. Not potassium that you consume on a daily basis, but isotope of potassium. Okay, and then after that, what is the thickness of the crust? So we'll come to it. Roughly around 30 to 35 kilometers in certain cases. What is the meaning of radioactive? Okay. So which can undergo nuclear reaction like uranium. You would have heard about plutonium. Nuclear reactors you would have heard about. You would have basically, if you would have heard about the nuclear bombs, right? So you have certain materials which exhibit radioactivity. They emit alpha, beta, and gamma rays, right? So that is radioactivity. So the basics of science, you will cover this and explain lithosphere. There is nothing to explain, my dear friend, in this, Lata. Lithosphere consists of the crust and the solid portion of upper mantle. That is what is consisted in lithosphere. Okay. Asthenosphere lies below the region of lithosphere. So lithosphere consists of crust plus solid upper mantle. That is what is included in lithosphere. Okay. Now we come to the written portion of the various different layers. So crust is the outermost solid part of earth. It is brittle in nature, in the sense that when we say anything is brittle in nature, it breaks easily. It doesn't have a lot of structural integrity. Whenever there is a kind of a push and pull that is induced, it can easily break up. So that is what you observe here. So it is brittle in nature, can break easily. It represents very less portion of the mass of planet earth, represents only 1% of Earth's mass. So, all the various things that you have seen in your life till now, all the various different rocks, mountains, etc. All of them which might have appeared to be the mightiest and the heaviest across the planet. In fact, those are amongst the lighter things when you consider the entirety of the planet as a whole. So that indicates or exhibits to you the amount of materials which are present in the crust. It is very, very light as compared to the inner layers. Thickness of the crust does vary under the oceanic and continental areas. Oceanic crust is thinner as compared to the continental crust, always. And basically, they are made up of different materials as well. Now, the mean thickness of oceanic crust is around 5 to 10 kilometers, whereas the mean thickness of continental crust is around 30 kilometers. However, in certain areas where you have the crustal compression going on, wherever you have, for example, the formation of mountains like Himalayas, there, because of compression, the crust has become significantly and substantially thicker. So in those regions, the crustal thickness can go up till even 70 kilometers from the surface. So the continental crust is thicker in areas of major mountain systems, such as 70-kilometer thick in the Himalayan stretches and the Himalayan areas. Now, the continental crust basically is composed chiefly of granite and has a density of 2.7 gram per centimeter cube. So it is lighter. Density is less means it will be lighter. And oceanic crust is basically basaltic, dark colored, iron filled, basaltic in nature. Mean density is around 2.9 to 3 gram per centimeter cube. This is a particular fact which is mentioned incorrectly, or which is mentioned as wrong in the NCRT. So please correct it. In NCRT, this is reversed. NCRT, as per NCRT, it will give you the idea that continental crust is more dense, but that is not the case. So correct it up in your NCRT as well. So, when we talk about this particular continental crust and the oceanic crust, continental crust is much thicker than the oceanic crust, but it is the oceanic crust which is always going to be heavier because the density is greater. Always remember that. Oceanic crust is always heavier than continental crust. And why is that? Because of higher density. Due to higher density. So, how is that the case, or why is that the case? So, for example, let's suppose, if you consider as an analogy, let's suppose you keep a slab of steel or iron, right? Along with that, let's suppose you keep a very thick block of thermocol. Now, the iron slab or the steel slab that you have, it will be much thinner than thermocol, but still it will be heavier than thermocol, isn't it? Thermocol, regardless of how thick you keep it, generally it will be lighter than the iron itself. Why? Because thermocol, the density is less, iron, the density is high. Similarly, in the case of the oceanic crust, the density is higher. That is what makes the oceanic crust heavier. Always in comparison to the continental crust, oceanic crust will always be heavier. Parshuram, 160 to 400 kilometers is the thickness of the asthenosphere. No, it is at that depth from the surface that you will find the presence of asthenosphere. Okay. Ajay, we can have that particular doubt at the end of the session. Now is not the time that we start talking about the optional subject. I'll remind me at the end of the session. I'll help you with the materials required for the optional as well. Now, then comes one of the bulkier portions in the interior structure of the planet Earth, and that is the portion of mantle. So, the portion of the interior beyond the crust, that is called as the mantle. Now, mantle starts extending immediately beneath the crust, and it extends up till a depth of around 2,900 kilometers. So, think about it, thousands of kilometers. Now, it is in solid state. Other than asthenosphere, it is in solid state. But this solid state that you will observe, again, I want you for a moment to have a utility of your imagination. This is not the solid that, for example, any of the solid objects that you see a solid object like a pen, like this, or let's suppose this remote that you observe, not that kind of a solid. A solid which can undergo some amount of compression, expansion as well, where materials, when they start melting, they can rise up. The colder materials somehow they make way and sink down, other materials fill that region. So it is that kind of a solid. That is why I gave you the analogy of a coconut. The inner flesh of coconut, if you press it, it can be compressed. But if someone asks you, in what state is that inner flesh of coconut present, is it solid, liquid, or gas? It is solid, isn't it? So that kind of solid with high density, very heavy density, much higher than crustal layer. Okay, it represents close to around 68% of the Earth's mass. That is huge. Okay, it has a density of around 3.4 gram per centimeter cube on an average. But as you start going into the lower regions of the mantle, automatically the density keeps on increasing. Density always increases with depth, increases in the lower portion of mantle. And why is it that the density increases? Because of increased pressure exerted from top, due to increased pressure from top. Is the presence of water a major factor for high density in oceanic crust? No, absolutely not. Can this number come in prelims because they are too much? No. The numerical factors that you see here, 3.4 gram per centimeter cube, 68%, 1%, 2 gram, 2.7 gram. No, these are not required. It is in, please understand slowly and steadily as you will read the different concepts of geomorphology, as you will revise it. This is something which is automatically going to stick in your mind. For this, you won't need to be opening book anymore. So in the mains answer, generally the candidates are able to reproduce these figures, but not to be asked in the prelims examination at all. Okay. Yes, Krishna, that is true. I am confusing in mantle and asthenosphere. Asthenosphere is a part of the mantle itself. When we talk about asthenosphere, it is present in the mantle itself, right? So upper portion of the mantle, below some solid areas, right? Below the lithosphere. So the upper portion of the mantle in general, because mantle extends up till a depth of 2900 kilometers. So something which is at a depth of 400 kilometers will still be considered an upper portion of the mantle itself, isn't it? So that upper portion of the mantle is called asthenosphere. The word astheno means weak. It is considered to be extending up to around 400-kilometer depth. It is one of the main source of magma, molten materials that finds its way to the surface during volcanic eruptions. Asthenosphere is present in the semi-solid, semi-solid, semi-molten state. Okay. So you observe the lower mantle below it, above it also you will find some portion of upper mantle which is present. Now then we come to the portion of the core. Now core is basically present underneath that mantle. So core in itself, the initiation of the region of core happens at a depth greater than 2900 kilometers or 3000 kilometers from the surface. That is where the core starts. And before core, many of us, we get a kind of a misconception that all the molten materials in the volcanic eruption, they come from the core. But here you observe that majority of the molten materials that you observe in the volcanic eruption, they are supplied through asthenosphere. It is those asthenospheric materials which start rising up, the presence of gases, etc. We'll study later about the intricacies and the nuances of volcanic eruption. You will get a better idea as well. So that is the portion of core. So core mantle boundary is positioned at a depth of 2900 kilometers from the surface. Okay. Core makes up close to around 31% of the earth, right? Now its density is higher as compared to the mantle in many of the areas as well. Inner core is in solid state, whereas the outer core is in a molten state, and the core is made up of heavy materials such as iron and nickel since the time of its formation, and hence it is also referred to as Nephe. Nephe, Ni represents nickel, Fe in Nephe represents iron. Hence the term Nephe is used for the layer of the core. Okay. Now, again, I will take you back a couple of slides. I take you back to this particular image here, the structure here. Now, here, if you pay attention for a brief moment, now as you go into the depth, let's suppose you talk about this region 1. And if I talk about another region 2, 1 is in the upper portion of mantle, 2 is in the lower portion of mantle, right? Now, when I tell you that the amount of pressure exerted at the region 1 is much lesser as compared to the amount of pressure exerted at point 2, I will be correct in making that assumption that the pressure increases by the time we reach the inner portion. Now, if the pressure is very, very high, the type of materials, the basic arrangement of layers, the particle arrangement, the density, everything will change, isn't it? So, for every layer, that is the region of crust, mantle, and even the core, as you go into the depth, suddenly beyond a point, you will observe the change in the material structure, the type of materials that are present. Because the same atoms of carbon, for example, if you arrange them differently, it will form coal. And the same amount or the same atoms of carbon under high pressure can also form diamond, right? So the same particles, when they experience very high amount of pressure temperature, they can form different materials altogether. So as we go into the depth of each of the layer, suddenly, due to pressure, due to temperature, the kind of materials, particle arrangement, their properties, everything starts changing. So that region where suddenly the materials, they start indicating a change, those are referred to as discontinuities. So that is what we have as discontinuities. So beyond a particular depth, the material structure, the pattern of it, the material property in itself, everything indicates a change. So even in crust, for example, between the upper layer and the lower layer of crust, the materials will change their state, they will change their structure, etc. And that is demarcated, that discontinuity is demarcated by what we refer to as the Conrad discontinuity. Okay, that is the Conrad discontinuity between the upper and the lower crust. Now the materials in the region of crust and the mantle, they will also be different. So that is demarcated by a discontinuity, that is Mohorovic discontinuity, or simply referred to as, that is also what is referred to as Moho discontinuity. Moho discontinuity. Okay, that is what we regard as Moho discontinuity, or simply Moho also is the term which is used in geographical parlance. Then, between the upper portion of the mantle and the lower portion of the mantle, you have what is referred to as the Repeti discontinuity. Then, between the mantle and the core, again, mantle is solid, core is liquid, there's a discontinuity, that is the Gutenberg discontinuity. And then outer core and inner core, the difference, that is exhibited by Lehman discontinuity, after the individual who first, for the first time, who came upon the conclusion that inner core could be in solid state. So it was after Lehman that the Lehman discontinuity came into existence. For your general studies prelims purposes, you should be aware about Moho. I will mark it as a star, Gutenberg, and Lehman. These three are relevant for the prelims for GS. Okay, these are the three which are relevant for the prelims purposes. Another set of or a type of question that is asked from this particular area is basically the abundance of materials. That when considered across the Earth's crust, which is the most abundant element which is present? When you consider the entirety of the planet, which is the most abundant element which is present? So that kind of question has also been asked in the presence priorly. So here, when we talk about the minerals in the interior, so there, when you consider Earth as a whole, the entirety of planet Earth, so iron is the most dominant one, followed by oxygen, followed by silicon, followed by magnesium, sulfur, nickel, and so on. Okay. Ideally, it would suit you if you are able to recall four of these, first four of these in order, that would be more than sufficient. When we talk of the minerals present only on the Earth's crust, oxygen is the most dominant one, followed by silicon, followed by aluminium, followed by iron. Now, this oxygen that you see, this is not the oxygen that you see in the air around us. This is the oxides. The oxygen which reacts with the various materials forms the oxides that is found on the rocks, rocky areas, etc. That oxygen we are talking about in this particular case. Okay. So that is also relevant for your examination. These are the person's names, obviously. Morovicic, Repeti, Conrad, Gutenberg, and Lehman. These are basically the scientists who came up with these particular findings. Okay. Now, before moving on into the portion of rocks, I would want to spend a brief fleeting moment into the portion of what we refer to as geomagnetism. Geomagnetism. Geo, Earth, magnetism, the magnetic field extended by or subtended by planet Earth. That is the meaning of geomagnetism. Now, planet Earth behaves like a magnet. Why is it so? That is because of immense amount of iron and nickel which is to be found in the interior around the region of the core. The amount of iron and nickel is huge, and the rotation of the planet further aids to that. So think about it. If in the interior solid iron and nickel would have been only present, no magnetic field would have been exerted. Let me repeat myself. If in the interior, rather than the liquid outer core, you only had the solid outer core of iron and nickel, no magnetic field would have been present. It is because of the liquid outer core that magnetic field is produced, right? So, magnetic field is produced due to liquid outer core consisting of iron and nickel. Iron and nickel. Now, why is it so that these will subtend or extend a kind of a magnetic field of action? Why is it that a magnetic field can be exerted or expressed or experienced because of this? So, understand this. So, here, let's suppose this is the planet. Let's suppose this is the region of core, the outer core, which is in a molten state. Now, the planet is consistently rotating on its axis from west to east. Continuous rotation happens from west to east. Now, the portion which is present in liquid, that will also move, rotate along with it. Not with the exact speed, not with the exact kind of collinearity or exact coupling, but then maybe if the outer portion or the planet as it rotates, some portion of the inner portion will also rotate, and so on. Nonetheless, in the region of outer core, we know certain facts. Iron and nickel are dominant, temperature is very high, and the material is moving, right? Again, iron and nickel are dominant in outer core. Temperature is going to be very, very high in the tune of thousands of degrees Celsius, and also materials are moving. So as the iron and nickel molecules, they end up moving at such high temperature, they tend to gain charge. There is production of ions in that region, right? So When those ions, they also move in a kind of a circular or a kind of a helical manner, what do? They produce a magnetic field, right? They produce a kind of a magnetic field of attraction. So that magnetic field basically is something that you will observe moving around. So it is because of a kind of a spiral or a helical motion that you observe in these ions which are created. Ions basically means the presence of charged atoms that are present, that are ions. Now, why do they have the charged ions or the presence of ions here? Because you have high temperature and material is moving. So it can happen that electron is lost or electron is gained by some other atom. So because of that electron exchange at high temperature and in movement, as the materials rub against each other, a charge is developed. Now these charged particles, they are moving in a rotational motion, so they will always extend a kind of a magnetic field as a result of that. So that is why the planet behaves like a bar magnet, and that is what is referred to as geomagnetism. Okay, but sir, magnet loses its energy if heated in science. But please understand, my dear friend, again, erase everything that you have thought or have a preconceived notion about. Think about it. This outer core by itself, had the planet not been rotating, this outer core by itself would not be regarded as a magnet at all. Okay? Outer core by itself, the presence of iron and nickel by itself would not have been regarded as a magnet. Okay, so here when we talk about the presence of, so you would have studied Fleming's rule, in case you are talking about science. So let's delve deeper into science. You would have read about the Fleming's thumb rule, that if the current flows in this direction, the magnetic field will be in this direction. Have you read about that, Srimant, or no? No. Have you read about solenoid or toroid in that case? No. Okay, don't worry about it. Just understand that when you have current which is passed through, this is a kind of a solenoid like structure. So when the current passes through like this, okay, when you pass current like this, now current moves in a kind of a spiral path, and that produces a magnetic field in this direction. Understand this particular basic fact. Here also, materials basically end up moving in a kind of a circular manner. Materials in the part, when we talk about materials here, we are talking about the charged particles of iron and nickel. They move in a kind of a spiral manner, and that produces a magnetic field. So here, ions of iron and nickel move in a spiral path, and that produces a magnetic field. Okay, as simple as that. You don't have to worry about what these models, what these diagrams are about. Yes, this is form of electromagnetism that you observe. Almost a similar mechanism is at play. Okay, see, I would not have gone into that solenoid or toroid, but then because my friend Srimant here said that in science, when you hit a magnet, it loses its magnetic field. So that is why I'm trying to convey here that this is the outer core is not a magnet. The inner core is also not a magnet. Had the planet not been rotating, magnetic field would not have extended. Had the planet's interior been completely in solid state, even after rotation, it would not have gained a property of a magnet. Only because it is in a liquid at a high temperature, there will be an atomic or electronic exchange which will happen, electron exchange which will happen, which leads to the formation of the charge moving around in circular path, and that is why the planet behaves in a magnetic field. Is that understood or no? What are the doubts that you have? Shrimant, Sidhya, Vishal, please let me know if this is understood or not. Okay. Himanshu, ionosphere are affected due to Earth's magnetic field or not? Not majorly, no. So that is what is referred to as geomagnetism. Now, the impact of this magnetic field, again, okay, do we need to so are we comfortable up till here, guys? Only then will I expand the concept. Otherwise, let's stick with the basic concepts of general studies, and you will also be much happier at the end of it. Because let me tell you, all these things that we have studied, let me hold a guarantee that you will not find it in any book. And most of you would have studied the various different books before coming the class also. So you would also attest to the fact that in this much detail and in this much depth, you will not find the analysis in the beginning of geomorphology for any book, even for optional that you pick up. But then again, that completely depends upon your comfort level. At any point of time where you feel that it is starting to become uncomfortable, we will pull ourselves back to the level of general studies, and it will be happy go lucky thereafter. And so please let me know. Kaustubh, is geomagnetism peculiar to the Earth in our solar system? In this case, yes, but there that is why more researches and space uh, odysseys in a way are required, space visits are required, because it is expected that few of the other particular moons of certain systems, they could also have they could also have magnetism, but how that magnetism would be subtended, that is something which is not known. Okay. uh, Impact of geomagnetism. What is the impact of geomagnetism? You would have operated a compass you would have seen always points to the north direction. Based on what? Why is it that the compass points in the north direction? Have you ever wondered about it? That why is it the case that compass doesn't move in the east, or doesn't show, or why will it show a direction at all? It is dependent upon geomagnetism, right? So even when we talk about the birds that carry out the migration pattern for thousands of kilometers overall, now it is estimated, it is still not proven in many of the cases, but it is still estimated that in their brain they have that natural system which aligns itself with the Earth's magnetic field, which helps them understand the kind of a path that they will take. So that is also a kind of a research which is going on. But there are other impacts also created due to the magnetic field. That is why I wanted to understand that whether you are comfortable up till this or not. So here, yes, Satish, that is correct. So here, first slightly deeper concept that we get into. When you are imagining the liquid form of iron and nickel, I hope you are able to understand and you are able to imagine that this liquid will not be like the liquid water that you see in your surrounding at your homes. This liquid will be significantly in a way of having certain lumps which can flow, right? Certain areas which are denser, certain areas which are less dense. That kind of a liquid is there. Now, why am I telling you this? I'm telling you this because it can also happen over a period of time, over a few hundred years, over a few decades itself, that those lumps, they start concentrating in certain areas of outer core. Lumps of liquidy iron and nickel, they start concentrating in certain areas. or they might simply shift as like a bubble from one region to another. This can happen. You can have your imagination like this, that this can absolutely be possible. Whenever this happens, the magnetic fields, the magnetic poles of the planet, they undergo a shift. The last time it happened was in 2020, when the magnetic North Pole actually shifted from the region under Alaska, Alaska is in North America, to a region under Siberia. That is because it was expected that a large iron nickel liquefied lump from the outer core, it has slightly shifted. It has taken a long time to shift. It has been happening for many years, but finally it has shifted, due to which the magnetic field suddenly changes. So ever since the history of evolution of planet Earth, there have been hundreds of such incidents, thousands of such incidents, where the magnetic field of the planet, the magnetic poles of the planet, they have changed their structure, they have changed their place also. Okay, so this is to tell you that the magnetic poles of the planet Earth that you see need not coincide with the geographical north and south pole. It will generally be closer to it, but need not coincide with it. Okay, now another concept. So here, when we talk about planet Earth, when we talk about planet Earth, now planet Earth is nothing but a kind of a miniature ball in front of the giant sun, isn't it? When you consider the sun is many thousand times, millions of times larger than Earth. Now here, frequently, as you will study in science, the sun keeps on emanating charged particles in the form of what we refer to as solar winds, what we refer to as a coronal mass ejection. So the charged particles, plasma, etc., they keep on traveling and they are emitted by the sun. They travel at very, very high speeds of thousands of kilometers per hour. That is the speed by which they travel. Now here, these charged particles, they are basically influenced by the magnetic field. Okay, these are basically influenced by the magnetic field which is exerted by planet Earth. Now, all these charged particles, they basically end up getting diverted to the region where the density of these magnetic fields is going to be the highest. That is where they keep on getting diverted, where you have the very high density of these magnetic fields. Now, if I ask you, where is it that the density of magnetic field is highest? Is it this point 1 or is it this point 2? Where do you think that the density of magnetic field lines is higher, 1 or 2? What do you think? Obviously, not much point of contention. That is basically the region of 2. That is where you will find very high amount of incidence of magnetic field of action. So all these charged particles thereby, let me represent the charged particles by a different coloration. So all these charged particles, they get diverted. That is a part of the solar wind, the coronal mass ejection, etc. They get diverted and they interact with the Earth's atmosphere around this area. Charged particles emanated by the sun, released by the sun. Movement is done only through the medium of air. How movement is done in vacuum? The force with which sun basically expunges or releases these materials, right? It is initially all of that, you will study in science in detail, Zabir, so I don't want to go into the depth of it. Basically, in the sun, you have a magnetic anomaly which develops in the form of sunspots. You have dark areas on the sun, which is referred to as sunspots. Around that magnetic anomalies and the charged particles, they form a kind of a ring of sorts, and then they are later expunged or released by the sun. That takes the form of a solar flare or a coronal mass ejection. And because they are basically expelled by the sun with such high force, that is why they are able to travel with such high speed. And because it is vacuum, so that is why there is nothing to moderate their speed as well. It is only when they start encountering the gravitational waves of the planets and also the magnetic fields of the planet, in the case of the Earth, that is when they start getting deviated. It is the deviation, the angular deviation of these charged particles, that is one of the purpose why we have launched the Aditya L1 mission. So amongst the various purpose of Aditya L1 mission is also to understand how that angular variation of these charged particles happen. Okay, so here all these charged particles, then they come across these areas where the magnetic field lines are of greater density, and the charged particles interact with the charged particles interact with oxygen and nitrogen molecules in upper atmosphere. Now, immediately you can imagine a particular molecule is lying in peace, resting in peace, chilling out. Suddenly, a charged particle from the sun hits it. What will happen? Electron will either jump away from it or electron will come back to it. Whenever that process happens, where from oxygen, nitrogen, etc., the electrons either they jump away from the molecule or come back to the molecule. At this particular stage in the atmosphere, in the presence of the magnetic field, that produces light. Light energy is produced upon that interaction. Okay, so this interaction produces light energy. And that light is what we observe in the form of auroras, not aurora. One of you have written Aurora. Aurora is a Punjabi surname, right? Don't confuse it with Aurora. It is auroras. So these are basically also referred to as northern lights. Hundreds and thousands of tourists, they visit the places closer to the poles in order to witness these northern and southern lights. Northern lights in the northern hemisphere, or what is also referred to as aurora borealis. And this is also what is the southern lights or aurora australis, observed in higher latitudes. Higher latitudes. Is that understood? Can we say if debris came in the area of geomagnetic force, Earth attracts them? Geomagnetism, not significantly, but if it comes under the gravitational pull or the gravitational range of the planet, yes, it will attract them. Can we expect a solar flare from sun greater than the Earth, which can impact Earth drastically? Yes, always. So these things have happened. What is referred to as the solar maxima and minima. So sun basically operates on what is referred to as an 11-year cycle, where after every 11 years, the solar activities they simply flare up. So that is when you have a lot of slow solar flares which are released. and that impacts the satellite systems. Many of the satellites, they get damaged, the communication systems on the planet get damaged, the electrical lines of communication that you observe, now they also get short circuited many of the times. So overall, the if we take it on a lighter note, so all the impacts that you see in the very famous Hindi movie where you had the, or the Bollywood movie where you had the UFO coming in, right? And basically the impact created by the alien people, that is the impact that is created by solar flares in general. Okay, I'm sure all of you or most of you would have heard about that. So that is basically what we refer to as auroras. However, if you are interested to know more about it in greater detail and in greater depth about it, I would suggest to you that on the YouTube channel, I had put up a video when this event was quite pervasive and quite prominent a year back or a couple of years back, and you had the occurrence of space hurricanes. So you can check out that video on our YouTube channel. So you can always go for that. So I will write here in for your reference if you want, if you are interested in. I'm not someone who will impose a burden on you. Space hurricanes. Do look at this, and this is present on our YouTube channel. Okay. Suggest some movies which are relevant to our subject for the weekend. I won't be able to suggest a movie as of now, but I would be very much able to suggest a documentary if you are interested in that. So, Cosmos is one of those documentaries that you should watch, right? And yes, aurora is also observed on other planets. That is true. So Cosmos is one of those documentaries. So the Carl Sagan one is quite old, so that obviously you won't be able to follow. But the newer one, that is by Neil deGrasse Tyson, the physicist who was involved in denaming of Pluto as a planet, he has basically hosted that a series of Cosmos. You can watch that. You will get an idea about the formation of the universe, the formation of the solar system, the existence and the occurrence, origin of life. So, Cosmos is one of those documentaries that I always suggest. Okay. Is this portion clear? Any doubts that we have till now? Good. And is gravitational force or gravity of Earth pulling object towards it, or magnetic force of Earth, or both? See, the charged particles basically, Lala, I think it was your question. Yes. So the charged particles basically, the charged particles will be attracted more by, or it is not attracting, but it is getting deviated. And then it is focusing upon the magnetic field, right? Now, the charged particle released by the sun, that will travel the entirety of the solar system, if possible. It travels furthermore. It travels, or in many of the cases, travels to the farthest reaches of the solar system also. But then, around the region of Earth, it will impact the region around the area where the magnetic field lines are greatly incident upon, where the density is very, very high. Okay. Cosmos, some of it would be available on YouTube also. Otherwise, I think it is available on one of the OTT platforms. I don't remember or recall exactly. I think it would be Hotstar or something. So one of the OTT platforms has that Cosmos. So you can watch that. Okay. Now, after this, we come to the portion of rocks. Now, rocks are the things that we come across on our day-to-day lives, on our day-to-day basis, when even when you step outside your house, let alone anything. When you step outside your house or when you visit some place, you would have come across various different types of rocks. You would have come across certain rocks which can break easily, certain rocks which are very, very hard, certain rocks which are darker in color, certain rocks which are lighter in appearance, certain rocks which are lighter in weight, certain rocks which are very, very heavy, right? You would also have heard about those particular mythical stories about certain rocks which tend to float. You would have observed also certain rocks which tend to float, right? When you go to Rameshwaram, there you encounter such kind of rocks which have the tendency to float as well. So rocks, they basically, they form the structure of the planet's surface from the outside, and these are basically aggregates of the various different minerals which are present. All the various different minerals which constitute the rocks, they end up pertaining, or they end up giving the properties or the characteristics to the various rocks. So rocks are basically the mineral aggregates with a combination of properties of all the various different mineral traces. Any unique combination of chemical composition, etc., that is a characteristic of a rock. Now, based upon the criteria of formation or the conditions in which they get created, they are classified into three basic types. You have the igneous, sedimentary, as well as the metamorphic rocks. Now, the igneous rocks, these are the primary rocks. These are the rocks which were created for the first, right? Now, these are created when? Igneous. Igneous refers to a term which is closely associated with fire. That is where the term igneous has come from, isn't it? So when we talk about igneous rocks, these are those rock structures which get created by the cooling down of lava or magma. So you can imagine the first rocks created on the planet's surface, they would have been igneous rocks. Hence, these are also what are referred to as primary rock systems. Okay, so these are also what are referred to as primary rock systems. Created due to solidification of magma or lava. Now, here, when it is created due to solidification of magma or lava, will it consist of organic materials within it? That is the remains of plants, animals, fossils of plants and animals. Will that be included in this? No. Why? Because it is the molten materials which are coming from inside that is solidifying, right? So here, that is why you won't find the presence of organic materials or organic elements to be found in the igneous rocks. They are particularly hard. There is also a sub classification of igneous rocks, etc., that we will study tomorrow. Sedimentary rocks, these are basically created by the compaction and the solidification of deposits. So, in a region, now think about it. Let's suppose you would have encountered some soil in your garden. Leave it out there. Okay. Don't tend to it. Don't pour water into it. After some time, if you take a look at that soil, it becomes very, very hard, almost like a rock. So similarly, the deposits which are made by the rivers, by the wind, etc., over a period of hundreds and thousands of years, these particular deposits on top of each other, due to the weight imposed by each other, they start to solidify and they form the sedimentary rock. That is, they are made out of sediments. So various different deposits, different types of deposits. They don't have a uniform structure at all. So that is because of solidification and compaction of sedimentary sediments or deposits. Now, either the igneous or sedimentary rocks, when they are exposed to extraordinarily high temperature or pressure, they change their state, in the sense that the particle arrangement changes, the rock characteristic also changes. And that is when we say that the rocks have metamorphosed. They have changed their shape, they have changed their nature, and you get metamorphic rocks. So when you have igneous or sedimentary rocks or any kind of rocks, so rocks when exposed to very high temperature or pressure, they change the particle arrangement, nature, property changes, and We observe the formation of metamorphic rocks. Okay, so that is how you have the basic classification of rocks. Said igneous rocks, by cooling down of the molten materials which come from the inner portion of the earth's surface. So by cooling down of magma or lava, you get the formation of igneous rocks. By basically the deposits of the sediments which get solidified, you get the sedimentary rocks. And when you have the particles, the materials, or any kind of rock, when they undergo distinct amount of exposure to temperature or high temperature or high pressure, their state changes, their particle arrangement changes, the characteristic changes, and they form metamorphic rock. We will study in much greater detail about each one of them tomorrow when we study their types, their characteristic, their nature, their classification. That is something that we are going to study tomorrow. Okay. Early man produces fire from igneous rock, or the other metamorphic rock can also produce fire. Okay, and some types of sedimentary rocks also, when you rub against each other, they can produce fire, but it is not something which is restricted to it. Okay, and now let us take certain doubts. Shiva, if auroras are observed in other planets, does it happen in the presence of oxygen? No, the other gases end up reacting and producing that in the process. Okay, so that is where we'll restrict the classes here today. We'll take up a few doubts and we meet again tomorrow morning at 10, where we continue this furthermore. Can we say that all the rocks found on planet Earth are formed from lava or volcanic activity? Initially, yes, but then the igneous rocks over a period of time, they can get disintegrated, they can form sediments, they can lead to the formation of sedimentary rocks. Igneous rocks, so the present day you have sedimentary rocks also, metamorphic rocks also, right? So primary rocks at one stage of time, all of them were igneous rocks. And Himanshu, sir, add some information in slide regarding geography optional and some book authors. Okay, book authors for geography optional or general book authors that you are asking about? Please also take some quiz for assessment. Hmm. Which kind of quiz do you have? The PYQs do you want, or the things that we have studied? Okay, for optional, one of you had otherwise also asked. So for optional, if I have to suggest to you, absolutely. So basically, see, in the portion of physical geography, I will take you to the depths in many of the cases that for optional, you don't have to struggle much more. But still, for optional, for physical geography, refer to Savindra Singh. Okay. For Indian geography, you can refer to Kuller. But don't rely on Kuller for facts and data pointers. Rely on current affairs for uh, the data pointers and facts. Okay. Then after that, models in human geography. Human geography, for this, you can look into Majid Hussain. Then perspectives in geography. You can go for the thin book of R.D. Dikshit. Right? And selective study of the economic and social geography by Rupa publication. And social geography, that is by Rupa publication. That is also for selective study. Other than that, the magazine that you generally follow for general studies, in the magazine, the down to earth that you follow, that is something that you should follow as a must. Okay. Now, which type of rock, when exposed to high temperature or pressure, changes to metamorphic? Igneous or sedimentary? Any of them can change. For GS, PPT, and NCRT is enough? Yes. Can we say that Jupiter will have more magnetic field? No, we cannot say that. Anuj, I have a suggestion. Please start with some questions based on previous class, whatever we have learned. Okay, but then there are certain issues in that, Anuj, because in that case, many of them they would not have attended the previous session or something like that. We'll try to take the questions of the PYQs. You will have an analysis based on that. Okay. So that is where we'll end the session here, guys. I hope the session has been productive and informative for you guys. And I hope that at the end of the session, you are extracting something that you did not know before or an approach that you did not know before. We carry on this particular approach further tomorrow. Tomorrow is when we will delve further deeper into the portion of geomorphology. Till that point of time, do relax, take care of yourself. Goodbye, and have a good night. Thank you.